In this part we want to go through some basic definitions of graphs that we will need throughout the lecture. So, in general, our graphs are called G, and the vertex set is V, and the edge set is E. If I don't write anything else, then you can assume that this holds true. If we look at a single edge that's between two vertices U and V, then we say that this edge is incident to these two vertices. We say that the vertices are end vertices of this edge, and they are adjacent to each other. So U is adjacent to V and V is adjacent to U. Also, they are neighbors. So U is a neighbor of V, V is a neighbor of U. And we can also write, for example, all neighbors of U, or we can write every vertex that's adjacent to U. That's something that you will see a lot. If we look at the single vertex, then we can define the degree of the vertex as the number of edges incident to it. This gives us our very first lemma, the so-called handshaking lemma. The handshaking lemma says if we sum up all the degrees of all the vertices, then what number do we get? What do you think? Do you know? But if we sum up the degree of all vertices, then we count every edge exactly twice. We count this edge E once for U and once for V. So we get 2 times the number of edges. And this already gives us the first property of a graph, namely that the number of odd degree vertices in any graph is even. Because if you have an odd number of odd degree vertices, well, then the sum here is odd, and this cannot be because 2e tells us it's even. We often use paths, and for paths it's always not so clear how do we define the lengths. So for us, a path between two vertices of length L is a sequence of L plus 1 vertices, or L edges. So if we look at this path here, this is a path of length 1. There are two vertices U and V, and there's one edge. And this path here is a path of length 4. There are 1, 2, 3, 4, 5 vertices and 4 edges. If we have a simple cycle, then we have a UU path. And this must have at least one edge, otherwise it doesn't work. So the green and the green dotted here together give us a simple cycle in the graph, which is a path from U to U. We say that a graph is connected if there is a UV path for every pair of vertices. So no matter which vertices you have, it's always possible to go from one to another. In general, for two vertices, we say that they are reachable from each other if such a path exists. So this graph here is connected, but if I add this part here, then it's not connected because there's no path from vertices from here to vertices from there. We often use subgraphs. So a subgraph is just another smaller graph where the vertices are subsets of the vertices of G, the edges is a subset of the edges, and of course you can only have edges between vertices in B prime. So this here is a subgraph where you have these two vertices and this edge. Also this here is a subgraph. But also this here is a subgraph where we just add these vertices, but none of the edges incident to it. However, if we say that we have an induced subgraph, then we usually say this graph is induced by the vertex set. So we only pick a subset of vertices, and then we add all the edges between them here. So there we don't have a choice to leave any of these edges out. Further, we say that a connected component of a graph is a maximal connected subgraph. So what does that mean? We take all the largest subgraphs that are still connected. So this one is one of the largest subgraphs that are connected. We cannot add any other vertex or edge to it, otherwise it would be disconnected. And this is another connected component. So this graph here has two connected components. And generally, whenever we have a connected component, that means all the vertices inside this connected component are reachable to each other. So these are the basic definitions for simple graphs. In general, all our graphs are simple. So we don't have any multi-edges. That means we don't have many edges between the two vertices, but only a single one. And we don't have any self-loops. So we don't have an edge from U to U, but only from U to another vertex. If we don't say anything, then our graphs are undirected. So the edges are just sets of two vertices. But sometimes we also have directed edges, like here. There, in addition, we also have a direction of the edge. So we have a connection from this vertex to this vertex, but not a connection from this vertex to this one. So here it's important that our edge is not defined as a set of two vertices, but as a tuple, because we need the direction. And in addition to the definitions on the previous slide, we also say that U is the source of this edge and V is the target. So an edge always goes from the source to the target. Instead of defining just the degree of a vertex, we can now also define the in degree and the out degree. So the in degree tells us how many edges go in, for how many edges is this the target, and the out degree says how many edges go out, for how many edges is this the source. There's an extended version of the handshaking lemma here that we can use. And that tells us that if we sum up all the in degrees and we sum up all the out degrees, this is the same number. And it's exactly the number of edges. I think you can prove this yourself. This is quite straightforward. Instead of just having paths, we can also say that our path has to be directed. So now we can only follow edges in their direction. So this would be a directed VU path, but the blue edge does not give us one because it's in the wrong direction. Also, we can have directed cycles, where also the direction has to be fine. So the green one here is a directed cycle, but if we look at this cycle here, this is a cycle in the undirected graph, but here we cannot complete it, because if we follow the green edge and then the green edge, we cannot take the black edge back because it goes in the wrong direction. We say that a graph is acyclic if there is no directed cycle in this graph. So this one here is not acyclic because we have this green cycle and we also have this cycle here. But it's easy to make it acyclic by just removing this one edge. For connectivity, we have to be a bit more careful because now it's enough to have a directed path from U to V or from V to U. Although the whole graph is connected, V is reachable from U, but U is not reachable from V. So contrary to what we had before, a connected component does not give us that every vertex is reachable from every other vertex. These are the basics that we have for graphs, and in the next part we will continue with planar graphs and with planarity.